a very difficult question, right?
Yeah.
Okay, let's see if somebody has done it correctly.
Yeah, for sure, we have a lot of correct answers.
Yes, and then the answer, it's correct. The first one that I have here, it's the chat.
Wow, so many.
Is for Kushagra Singh, because he says a peer-to-peer VPN that the construct uses for remote controlling for remote lab. Yeah, okay, we use at the construct, of course, but it's you can use it in any other application for controlling remote robots, as Dominique was explaining before this morning. Okay, so Kusagra Singh.
Congratulations.
Congratulations, you're the winner.
Okay, so now let's welcome our last speaker, Iker Luengo. So Iker is a senior software engineer at eProsima.
Yes, and the talk about Iker is going to be a very hot topic in the ROS2 community related to the DDS communications. And he is going to talk about the zero copy transport in Fast DDS. Iker, are you ready for your presentation?
Yes, I am.
Yes, we're ready. Thank you very much.
I'm here with Daniel, a colleague of mine.
Okay, so Iker and Daniel, they are together on the same room, and they are going to do this presentation then together, right?
Exactly. Yeah. Thank you. Thank you very much for having us today. It's a pleasure.
Sure, our pleasure. The audience is all yours.
Perfect. Thank you very much. So as we just said, my name is Daniel. I'm part of the marketing team here at eProsima. And with me here is Iker Luengo. He's a senior engineer, and he will be showing you today the demo we have prepared. We'd like to start first with giving you a little bit of context on who we are, what we do at eProsima. Basically, we are a small enterprise that was founded in 2004, and we are middleware experts. To be more specific, we are focused on the DDS standard, which is a standard that was created by the Object Management Group, which is the OMG, a group of which we are members, and we are also contributors to the DDS standard. And we are also key contributors to ROS2. Actually, we are like the biggest contributors to ROS2 in Europe. And we are also members of the TSC, the committee inside of ROS2, and our middleware, Fast DDS, is also the default middleware in the long-term version of ROS2. So basically, this is who we are in a nutshell. And just to get to know a little bit better what we do, we're going to show you a little bit of some of our products. Our main product, the most relevant product we have, is Fast DDS, which is our own implementation of the DDS standard. It's open source, and we have developed many different tools and features around that. We also even provide commercial support for Fast DDS. We also have Micro XRC DDS, which is our DDS implementation for resource-constrained environments, which means for microcontrollers. And we also have products like the integration service, which is basically is a tool that enables the intercommunication between different protocols that speak different languages. But let's deep dive a little bit into Fast DDS, because it's the one that we are going to be using today. As we just said, it's an open source DDS middleware, and basically it's a public subscribed communication network framework. That allows the developers just to focus on the application logic, as it basically it takes care of the networking details. The Fast DDS is widely used in many different industries, such as robotics, IoT, defense, automotive for self-driving vehicles. Basically, in any industry that relies on high-performance network communications. And this is because Fast DDS provides, it's really easy to integrate. It allows interoperability. It provides high performance. You can check actually in our website different performance testings we have available. We have implemented many different QoS. We have implemented also the DDS security specification, so it's very solid, very secure. We support different platforms such as Windows, Linux, macOS, and one of the main advantages is that we have developed many different features around Fast DDS. One of them, for example, is the discovery server that we presented in this very event last year in the ROS Developers Day. And well, the discovery server is an alternative to the traditional node discovery. So this is a centralized node discovery process. And the main advantage that it brings is that it reduces the network traffic up to 93%. And some new features that we have developed this year are shared memory transport and zero copy. And well, my colleague here, Iker, will be telling you much more about these features that we will be using as well during this demo.
Okay, thank you very much, Danny, for the introduction. So yeah, we are going to focus here on the communication between ROS2 nodes and how we can improve that communication using the latest features that Fast DDS includes in ROS2 rolling. So I'm sorry that we are not going to have here any fancy visuals or 3D simulations because we are dealing with the middleware communications, but we are going to see how this communication affects the application. So as you know, in the most basic case, the data traveling from a publisher to a subscriber needs to be copied several times from the publisher application to the middleware, from the middleware to the transport layer, from the transport layer to the network, and then all the way up to the subscriber application. So especially when we are using large data types, all these copies may become a bottleneck in the communication. So fortunately, when the publisher and the subscriber are both run on the same host, Fast DDS offers several options to avoid using this network interface and thus avoid some of the copies, improving the communication speed. Not only that, but also Fast DDS automatically will select the delivery system that will minimize the number of copies according to the deployment that it detects. So just some examples. In the case when the publisher and the subscriber, they both run on the same host, the transport layer uses a shared memory segment to communicate the data. That's what we call the shared memory transport. And in that case, we are avoiding the copies to the network. It still needs copying to the middleware and the transport layer, so we still have some copies there. But we can improve even more that. If it happens that the data types that we are using are bounded in size, then we can use data sharing delivery. So in the case of data sharing delivery, the publisher keeps the history on a shared memory segment, and the subscriber can access the publisher's data directly on this shared memory segment. So we can avoid all the transport layer altogether and its copies. And finally, if the data types are not only bounded in size, but they are also plain data types, then Fast DDS supports borrowing messages from the publisher and the subscriber history. So this means that the application borrows a slot in the publisher's history, and then it writes the data directly in this slot, so that we avoid copying the data between the application and the middleware. So similarly, the same happens on the listening application, that it can access the subscriber's history directly without copying the data. So when the message borrowing is combined with the data sharing delivery, what we get is effectively zero copy delivery. One thing to note is that while message borrowing is automatically used in ROS2 RMW in the subscriber side, if the middleware supports it, the publisher side needs to be needs to explicitly request the loan of the slot. So what we are going to learn today is how to prepare the publisher for message borrowing and how we can use these features in Fast DDS with a careful design of the data type. As an example, to guide all this learning, we are going to use a very simple chatter with a talker and a listener. So the talker is going to try to send a message every millisecond. We also have the limit that the messages will always be smaller than 1 megabyte, although they can be of variable length. And both the publisher and the subscriber are configured as reliable and history with a keep all of size 1 configuration. So this configuration somehow simulates a high rate communication of large data. So not only that, but also the publisher will not be able to send a new message until the subscriber acknowledges the reception of the last one. So we can now open the editor and navigate to the ROS2 workspace directory here, and we will see how this chatter is implemented. So the first thing that we are going to examine is the data type, which is here in chatter data message. Sorry, I closed that message, chatter data message. And we can see that the data that we are going to be communicating between the talker and the listener contains an index that we are going to use just to keep track of the number of messages, and a sequence, a variable length sequence named data, which is the one that contains the actual data that is going to be communicating between the talker and the listener. If we go to see the talker, it's a very basic talker. We see that we are creating here a publisher on the chatter topic using the chatter data type that we just saw. Very important here, we are setting the reliability and the history to the system default values. And this is important because we want these values to be loaded from a profile XML file that we will see very shortly. So with this, what we are saying, the Fast DDS is okay. Take these values really from the XML file. More than that, we see that the talker is creating a timer every millisecond, and every time this timer triggers, we are trying to send a new message to the network. So the message, just for simplification, we are always going to send 1 megabyte message here. But the result will be just the same if we allow for variable length messages. Just keeping in mind that we want that message to be at most 1 megabyte. Also, we are not going to write the whole megabyte message here. We are just resizing the data and writing 1 byte in the last position, because we are not interested in the time that we spend in generating the data. We are only interested here in the time that it requires to communicate this data from one end to the other. So if we see the listeners, pretty simple also. We have again a subscriber here in the same chatter topic with the same chatter data type. Again, important, the reliability and history are set to the system default so that they are loaded from the XML file. And in this case, whenever the listener receives some data from the talker, what we are doing is just increasing the message in the received message number and printing some logs in order to show some progress. Also, when the subscriber finishes, it will provide a very crude estimation of the message rate that it received. So we can see here that we are taking a timestamp right before and right after spinning the listener. So and with this time span here, we are going to get an estimation of the number of messages that we received during this time in order to get the rate of the messages. So this is very, as I said, it's a very crude estimation. So it really is, it's not a very precise measurement, so we cannot use this for very formal throughput measurements, but for the sake of this example, it's enough, and it really does show the difference that we want to show. So the last thing that composes this example is the profile XML profile. This one, charted profile XML, and this file contains all the Fast DDS QoS configuration that we are going to use in both in the publisher and in the subscriber. So we are not going to show or review the whole file here. Only the relevant values are going to be reviewed, but you can refer to the Fast DDS documentation, which is linked in the notebook, I believe. Let's go back to the notebook. So you have here, you have the link for the Fast DDS documentation, where you can see the whole information about how these XML files work with Fast DDS. So back to the XML file. First thing to note is that every profile has a name, and important, if the name of this profile is the same as the name of a topic, that means that this profile is going to be used for the node that is publishing or subscribing in that topic. That means that this profile here is going to be used in the publisher for the chatter node, and this one in the subscriber for the chatter node. We also have some default profiles that will be used for any other nodes that do not have a specific profile for that specific for their specific topic. So let's see for the subscriber profile. We see that we have the configuration set as keep all with a depth of 1 for the history, as we described in the previously presented case, and also that the subscriber is set as reliable. And similarly, in the publisher, we have the same. The history is keep all with a depth of 1, and the reliability is reliable. In the case of the publisher, we also set the max blocking time to infinite. That means that whenever the publisher is trying to write a new sample and its history is full, then the write operation will block instead of failing. And that means that we are not going to be able to send a new message until the history, at least one of these slots in the history, is free, which occurs whenever the subscriber acknowledges the reception of that message. Also, then we have these values here, the resulting with QoS, which they control the memory allocations for the history for the publisher. And the fact here is that for 1 megabyte messages, the default values were too high, and we got into trouble with memory allocation. So we just reduced those default values for some other values that are appropriate for the case of a history depth of 1 and a single instance in the topic. So this example is already compiled in the workspace. So we are going to launch the example as is. We are going to open two terminals, one for the talker and one for the listener. And we have to move to the ROS workspace, ROS2 workspace. Workspace, sorry, there. Okay. And now we have to also set some environment variables in here in order for the example to work. So this first one is going to tell ROS that we want to use Fast DDS as the RMW implementation. And then we have these other two, which are telling Fast DDS that we want to load the profile files that's set here in this chatter profile XML file that we already saw. And we have to do this obviously in both terminals. Okay, let me copy this. Also, we have to source. We have to source both ROS2 rolling and the current workspace, because this functionality, at least the whole functionality, is only available right now in ROS2 rolling. Sorry. Yeah. Okay. So now we can launch the talker in the first terminal. Hello. Okay. Don't know what happened. There we go. So we can see. Let me just increase the size of the terminal. We can see that it locks the logs of the publisher. Since there is no listener subscribed to the topic yet, the publication rate will be fast because there is nobody listening the other side, and so there is no bottleneck at all, and you should see about 10 logs per second here. But when we launch the listener in the second terminal, now we can see that the log rate is much lower. In fact, we can go to the previous terminal to see the talker and see that it also slows the rate of the logs. And the thing here is that both these nodes are running in the same host, but the data type is not bounded. So they are using shared memory transport layer. And this is too slow for the expected 1,000 messages per second that we are trying to publish. So in fact, if we stop the listener, we should get that crude estimation of the message rate. And well, the values may vary, but note that the rate is much slower than the expected 1,000 messages per second. So what we are going to do now is try to convert this example to a zero-copy example and see the improvement in the communication. So the first thing that we have to change is the data type, so that we convert this data into a plain and bounded data type. So we go back to the chatter data message type, and what we are going to do is to change this unbounded sequence to a bounded sequence. We know that our messages are at most 1 megabyte, so we are going to set this into a 1 megabyte static size array, because we are not always going to, well, just in this example, but in general, we are not going to send always 1 megabyte size data. We are also going to add a new data field that's going to track the real amount of data that's going to be in that static array. That will be this data size here. And so now that we are using a static size array, we have to change the talker so that instead of reallocating the resizing the dynamic sequence that we had before, what we have to do here is just to set the real size that we are sending to the listener. So that would be data size equals sorry, I thought I was writing something down. 174. So with that, we just had, sorry, I copied this, that. So with this, we just adapted the data type to a bounded, size-bounded data type, and also we changed the publisher in order to use that. Not only that, but in this case, we also have a plain data type so that we can start using message borrowing also. Remember that we don't have to change anything in the subscriber, but we have to adapt the publisher in order to use this message borrowing. So instead of creating this message in the stack, what we are going to do is to borrow a message from the publisher. No, sorry, this message. We are going to borrow this message from the publisher, like so. And remember that now that the message is a borrowed message, we cannot access directly to the message fields like this. We have to get the reference first, so we are going to do that. If you are following these instructions on your side, you can just go and copy the whole callback from the notebook, and that will be much easier for you. I will go step by step here anyway. Okay, and remember also that we cannot just copy the message to the publisher, that we have to move it. Sorry, girl. Move. Okay, and I think that's all. So we are going to rebuild this chatter. So using any of the terminals that we already had. There we go. Again, remember that we did change the publisher in order to use the borrowed messages, but in the subscriber side, that's not needed because ROS2 already uses the borrowing automatically if the middleware supports that. Okay, so we are done. If we now launch the talker and the listener again. Okay, there goes the chatter, and there goes the listener. We can see that the logs are printing faster this time. And in fact, if we stop the listener, we can get the estimation, which is much close to the expected value of 1,000 messages per second. As I said, this is a crude estimation, so it's not very precise, but we can see the difference. So What's happening here is that now the talker and the listener, they both use a plain data type. Fast DDS is automatically using data sharing as the way of communicating both sides. And also we are using message borrowing, so everything is speeding the communication. And in fact, both the talker and the listener, they can keep up with the expected 1,000 messages per second. So using this kind of XML profiles, we can control the data sharing configuration further. For example, we can use something that we call data sharing domain identifiers to control which nodes communicate using data sharing and which do not. So even if the data types are data sharing compatible, we can restrict this data sharing communication only between some of the nodes. So, for example, okay, so let's try this, and let's go back to the chatter profile XML, and there we go. There we go. And we are going to add a new data sharing QoS field to both the publisher and the subscriber in the chatter topic. So just let me copy this thing here. And here below the QoS field, we are going to add this data sharing subfield. And what we are configuring here is that where we are going to keep this data sharing kind to automatic, which is the default one, is how it was working today, which means that, okay, if the data type supports data sharing, just use it, and if it doesn't support, don't use it. But then we are going to add these domain IDs. In the case of the chatter, this publisher and the subscriber, we are going to use a domain ID of 1234. We are going to do the same in the subscriber side. Okay, so the thing with these domain IDs is that those nodes that have at least one domain ID in common, they are able to communicate using data sharing. But those nodes that they don't have any domain ID in common, they are not going to be able to communicate using this data sharing. So for the moment, as we can see, this both they are going to be able to communicate because they have both the same 1234 domain ID. But we are going to set a new profile. We're just going to copy this chatter profile to another name, for example, gossip profile. And we are going to open this new profile, and we are going to change those values there. And for example, for the publisher, we are going to use the 5678 domain ID. And in the case of the subscriber, we are going to use both of them. That means that any subscriber that's using this profile is going to be able to communicate with both talkers using data sharing communication. So we are going to launch the same talker and the same listener again. There's one, and there's the listener. So nothing's changed here because these are the talker and the listener that are using the chatter profile, and they both share the 1234 ID. So they are communicating with data sharing at a fast pace. But now we are going to open two new terminals for another chatter, another talker, and another listener. Remember that we have to reconfigure all the environment as before. So I'm just going to copy everything here. There we go. But just note that instead of using the chatter profile, the first chatter profile, we are using here the second profile that we set, the gossip profile. That's the one in which the talker is using the 5678 ID, and the listener is using both of them. And if we launch the talker here, we can launch the talker immediately without rebuilding, because the XML files are loaded during the startup. So one talker. Okay, and if we go to the previous listener, we can see that now it's receiving, we can see that the logs have two log series intertwined. That means that it's receiving from both talkers, the fast pace one that's on the using the chatter profile, and this new one that's using the gossip profile. What's happening here is that this talker is using 5678 ID, whereas the old listener is using 1234. So they cannot communicate using data sharing. They are communicating using the shared memory transport layer, and thus they are again facing the same bottleneck that we saw in the first example at the beginning. We can also launch the second listener. Remember to configure everything. Okay, this line is not necessary. And launch the new listener. Sorry there. Okay, and here we also see that this listener is also receiving from both the talkers. The thing is that, again, even though this listener is able to communicate with both of them, remember that this one is the one that's using both IDs, even though this listener is able to communicate with both talkers using data sharing, the truth is that the throughput of the talker is limited by the slowest communication it is handling, and in this case, the second talker here has to communicate at a small pace with the first listener. So this new one is also receiving at a slow pace from the second talker because of that. So we can indeed stop this listener here. This is the one that's causing all the bottleneck. So if we stop this one, and we go back to the second listener, then we can see that it's receiving again fast from both talkers, because now both talkers, they only have a single listener listening to the chatter topic. And this listener, even though one of the talkers is publishing in one ID and the other one is publishing using the other ID, this listener is able to communicate with both of them, as we saw in the profile.
5 minutes.
Okay, thank you. So there are more things that we can do using the XML files in order to control data sharing. We can altogether disable data sharing. For example, we may need that in order to get some traffic logs in order to debug our system or whatever we want to analyze the traffic, which is not possible to do with the data sharing. So maybe we want to disable data sharing altogether. That we can do also using profiles. So that's as simple. And instead of using the automatic kind for data sharing, you can just turn it off, and then it will be disabled for these profiles. So that's also very easy to check very quickly. Let me stop everything here and relaunch again. This is the Cosip one. Okay, so let's go to this terminal that's using the Cosip one. So launch the Docker and launch the listener. And there we go. We are again using the shared memory transport. And again, we are not keeping up with the expected 1,000 messages per second. So that's basically all that we had prepared. There are many more things that we can do with the XML files, but again, I direct you to the links that are below in the notebook, where you can learn how and everything that can be done with these XML files and how we can use these XML files also on ROS2. We have seen that, Fast DDS automatically selects the best delivery mechanism according to the setup that it's used in your application and the data type that we are using, and how with a very smart design of the data type we can enjoy a zero copy delivery, and how to boost the performance of the application, minimizing the communication and maximizing the communication throughput, and how this is especially useful for applications with large data and high polishing rates. And additionally, we also have seen how to control the data sharing configuration using profiles in XML, and how these profiles are loaded during the setup of the node, which provides a convenient way of changing the configuration without the need to reveal the whole solution. And that's basically all. I hope you learned something today. And if you have any questions, well, I'd be glad to answer them.
Very good. Thank you very much, Iker, for your presentation. And now let's go for the questions to Iker. So we have already several questions here on the chat, actually on the questions tab of the conference. Then let me go. There are some others that are most voted, but I want to start one that is more relevant. I consider more relevant. I'm going to ask the others also, but it's one question by Jonas Mahler. And he's asking, so Fast DDS is intended for distributed systems, but zero copy delivery is only possible on nodes that run on the same local host. Is that right?
Yeah, that's right. In fact, you wouldn't have zero copy delivery in any distributed system, because in any case, you will have to go through some kind of network transport, and in order to communicate that data. But even in that case, there are quite many setups that are run on the same host. And in fact, here in eProsima, we have worked with some of them. And this is a setup that's occurring more than what we expected. And yeah, this is intended for the case in which these nodes are run on the same host. Mm-hmm. But yes, as I say, this happens more than what is at least expected at first glance.
Yes, that's correct. Okay, great. Then let me go to the most voted one of the questions, but probably you are expecting. And it's a typical question about what are the main advantages of using eProsima Fast DDS respect to Cyclone DDS plus i0x, and how should we choose between the two DDS implementations?
Okay, so basically, in the case of Fast DDS, you don't need to add anything else to what's there, because it's already built in the latest Fast DDS. And not only that, if your data model already it's already supported by the zero copy system, which means basically that it's a plain data and it's bounded in size, which basically if it's plain data, it's already bounded in size, but whatever. The thing is that it will automatically be used in your system without having to do anything else. So Fast DDS always tries to check the setup and the data type you are using in order to find the more appropriate delivery system that fits your system.
Okay. Then let me go with another question from Jajabalahi, that he's asking, how is concurrency handled? So the typical scenario in which the data reader reads before the data writer writes.
I don't know if I get the question correctly.
I understand that is because you're writing to the memory.
Yeah.
Then it's so while you're writing, maybe somebody wants to read, and I understand like this.
Yeah, I understand the concurrency problem. Don't know if this is exactly what he means, but basically there is some synchronization between the writer and the reader, and well, the thing is that the writer is not going to write any. So in Fast DDS, in the case of using data sharing, we don't only have the writer's history as a buffer, but we also have what is a pool for data changes. So this pool that we are using is usually or can be larger than the history itself, and even though the history in the writer works as in any other any other DDS application, whenever the pool of messages gets full in the writer, the writer is not going to be able to write a new message until the reader somehow acknowledges a new message that has been read. Mm-hmm. So that's whenever that happens with that acknowledgement, that's how we can control if the reader already got this message or not. Okay. And more than that, also in the message itself, there is some metadata that we are using so that whenever the writer wants to recycle any message in that pool, because okay, so we are just writing and imagine that we have some kind of keep last configuration in which the writer is never going to be blocked. So whenever we are going to reuse a message in that pool, we are going to mark that message as reduced. And in that case, the reader, if it accesses that same message, because it has it in its history, it will know that this message is overridden, and then it can do whatever you tell him to do with that message that is already overridden. Basically, what will happen is that, okay, so this message has been removed from the history, and it will dismiss it.
Okay, makes sense. Yes, it's a little bit complicated mechanism, but it makes perfect sense.
It's difficult to explain it the whole right here. Because it really, the synchronization mechanism for this was quite difficult and quite hard to get, and it has many sites. But yeah, basically, so I hope that something just was, you understood something at least.
Okay.
Sure.
Okay. Okay, so we don't have more time for more questions. Then we have to thank our speakers again. So thank you very much for your time and see you around the universe.
Thank you very much.
Thank you very much.